Hello and welcome back for section 8.2. We are still working on confidence intervals and we're still going to be completing a confidence interval for population mean, mu, but this time the mean and the standard deviation are unknown. So we do not know the population standard deviation. So that's the difference between 8.1 and 8.2. So because we are estimating the population standard deviation to be able to create a confidence interval for the mean, we have to use a different distribution. It's slightly skinnier. It's called the T distribution. So T distributions are found by knowing your area that you want and what's called the degrees of freedom. So we have to offset our curve a little bit because we're estimating our standard deviation. And so we're going to take our sample size and we're going to use what's called the degrees of freedom here. And the degrees of freedom is equal to the sample size minus 1. So the T distribution is similar to the normal distribution. It looks very much almost the same, but there's just a few differences and not much is different, but it's still centered and symmetric around 0. The area under the entire curve is 100%, just like it was before. The area to the right of 0 is equal to the area of the left, which is equal to 0.5 or 50%. And the x-axis is a horizontal asymptote. So it looks very much like the normal curve, it's just a little skinnier. I'm sorry, it's more spread, it's a little more spread out. Sorry about that. It's just a little bit wider. But the bigger the closer that our sample size gets to 30 becomes, it becomes the same shape as normal. Okay. So let's just jump into the samples. So there is going to be a link in Canvas for all of the work for 8.1, I'm sorry, for lesson 8.2 and in Desmos, and there every example has its own folder so that you can see all the work there. So if you want to go there and follow along, I'm also going to introduce a link in Desmos that will help you calculate confidence intervals very quickly. Okay, so let's look at example 1. It says, suppose you do a study of acupuncture to determine how effective it is in relieving pain. You measure sensory rates for 15 subjects with the results given. Use the sample data to construct a 95% confidence interval for the mean sensory rate for the population from which you took the data. The solution is shown step by step. So you can use a TI-84 calculator if you want. I'm using Desmos. We put the data into our table in Desmos. And this is to find the confidence interval. You're going to need the sample mean and the error bound of the mean. Our sample mean is 8.2267. Our sample standard deviation is 1.672. So we have to find both of those now because we're not given the standard deviation any longer. Our sample size is 15. So our degrees of freedom is 15 minus 1 or 14. And our confidence level is 95. So our alpha is 1 minus 0.95 or 0.05. And our alpha divided by 2 is 0.025. So to find our T of alpha divided by 2. So in 8.1, we use the Z, critical Z, we're using the critical T. And to do that, we can use our TI-84 similar to what we did in 8.1 using inverse T here. I'll show you that. So we would go to second inverse, and you're going to choose inverse T instead of inverse norm. And then it just asks you for the area. So you're going to do the area to the left, which is 1 minus the 0.025, 1 minus 0.025, and then our degrees of freedom, which is 14, and hit paste and run. And it'll take a minute for it to generate because it's generating this every time. So 2.14. We can also use our formula packet, just like we did for the normal curve. And we take our area 0.025, we go to the top 0.025 and then down to the degrees of freedom. So it would be 0.025 down to row 14, and there we get 2.145. We can also use Desmos. So let me go and show you. There's a Desmos link for the T-curve in Canvas for you. But this is what it's very easy to type. It's just TDAST, and then you put your degrees of freedom. And right here, so it's inverse T distribution. And you put your degrees of freedom, 14, and then your area that you want, 0.025, and this is going to be the negative, remember? So if we did 1 minus that, it would give us the positive, the 2.14. So I'm going to write that on our paper for us. So inverse CBF parentheses TDIST parentheses degrees of freedom, comma, the area that you want. Okay. So I'm also going to show you, this is what it looks like. So example 1 here is the acupuncture. And if we click on that, you can see I entered the data into my table, and then I found the mean and the standard deviation from there. Okay. And then we calculated the mean by taking your T, and that's formulas here, your error fund formulas right here. So your T, which is the 2.14, your standard deviation from the sample, and then the square root of n. Make sure you use the square root of n, not the square root of the degrees of freedom. So our error bound is 0.924. So our lower and our upper are 7.3 and 9.15. So an interpretation would be the 95% confidence interval is 7.3 and 9.15. We estimate that with 95% confidence that the tree population mean sensory rate is between 7.3 and 9.15. Now, you can also use in Desmos there is I made a link in Canvas. It says confidence intervals for one sample. And so it says enter the sample size. We entered 15. Enter the sample mean. So I put that there. Enter the sample standard deviation. Enter your H0. So you don't need that for the confidence intervals. You can skip down here to where right here, this that where it says confidence interval. So you don't need any of those except for the confidence interval. So you're going to click on that one, and then you're going to go down and you're going to enter the alpha. So alpha is 1 minus your confidence level, and ours is 0.05. And so when you click on the confidence interval tab, you're going to scroll down, and there will be an LB, that's your lower, that matches our 7.3, and the UB, and that's our upper. So we're learning how to do the pieces on our paper, but this will calculate them quickly for you using the t distribution. So let's look at example 2. It says you do a study of hypnotherapy to determine how effective it is in increasing the number of hours sleep subjects get each night. You measure hours of sleep for 12 subjects with the following results. So we're going to put those in Desmos, and n is 12. So that means that n minus 1 is 11, and this is our degrees of freedom. So we need to find the mean and the standard deviation. Open this up. So there's our data, and we found the mean to be 8.98. So I'm going to write that on my paper. And the standard deviation of our sample is 1.29. And for our T, our critical T, we just had to put in 0.025 because it's a 95%. So so we can find our area as 1 minus 0.95 divided by 2. That will tell us that it's the 0.025. And then we put in our degrees of freedom. And so our T is, and we can put it as 1 minus that. So it's so you can see it's a positive. It's not, notice it'd be just a negative, we left it that way. Okay, so our T of 0.025 and degrees of freedom 11 is 2.2. We'll call it 2.201. Okay, so let's see what we have in our paper so far. So we have our sample mean, our sample standard deviation, our sample size, our degrees of freedom. Define the random variable in words. So X is number of hours of sleep per individual, and X bar is average hours of sleep for the sample. And it says which distribution should we use and why. So we're using the T because standard deviation is unknown. Construct a 95% confidence interval for the mean number of hours slept for the population. We're trying to predict that using the sample data. So calculate our error bound. So our error bound of the mean is going to be our T of alpha divided by 2 times the sample standard deviation divided by the square root of n. So it's 2.201 times our sample standard deviation of 1.29 divided by the square root of 12. Okay, and so our picture, we're going to just draw that. This is going to be our 0.025, 0.025, and 0.95. Remember, these have to add to make 1. And this is our confidence level. And so this is our negative t, and this is our positive t. Let's go to our Desmos to see this. So there's our error bound margin calculated. It's 0.8196. And then we're going to find our, this is our lower, and then we're going to find our upper. And so 8.163 is our lower and 9.80 is our upper. And we can validate that using our little format program here. So we can put in 12 as our sample size, and the mean number of sleep was 8.98, and the standard deviation of sleep was 1.29, and our alpha is 0.05 again. And so we can scroll down to our lower, there's the 8.16, and there's the upper 9.79, all rounded to 9.8. So there we are. Interval. It's right there. So we are 95% confident. The true hours of sleep from the hypnotherapy is between 8.16 and 9.8. I showed the pieces here, and then we can use that computer entry in Desmos to find it. Let's do another example. This one is on the Human Taxonomy Project. It's working to understand the scope of industrial pollution. Industrial chemicals may enter the body through pollution or as ingredients in consumer products. In October 2008, the scientists at HTP tested cord blood samples from 20 newborn infants in the United States. The cord blood was tested for 430 industrial compounds, pollutants, and other chemicals, including chemicals linked to brain and nervous system toxicity, immune system toxicity, and reproductive toxicity and fertility problems. There are health concerns about the effects of some chemicals on the brain and nervous system. The table shows how many of the targeted chemicals were found in each infant's cord blood. Well, that's so. It says use a sample data to construct a 90% confidence interval for the mean number of targeted industrial chemicals to be found in an infant's blood. So I kind of did the work here for us just so we could quickly go through another example. All of the work is in Desmos if you go and click under that folder and open that folder. So our degrees of freedom is 19. Our confidence level is 0.9. So this time our alpha is 0.10 and alpha divided by 2 is 0.05. So degrees of 19, degrees of freedom of 19, and 0.05 is going to be right here, 1.729. Right here. The error bound of the mean is the t, the sample standard deviation calculated from decimals in the square root of n. And then we're going to subtract and add that from the sample mean of 127.5. So we estimate with 90% confidence that the mean number of all target industrial chemicals found in cord blood in the US is between 117 and 137. Yikes. Another one. Oh no. A random sample of statistics students were asked to estimate the total number of hours they spend watching television in an average week. The responses are recorded in the table below. Use the sample data to answer the following. So we need to find the sample mean, the sample standard deviation, the sample size. So it says 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. So our degrees of freedom is 14. And so let's go ahead and fill in what we know. So X is number of TV hours per individual. And then this is the average number of TV hours per sample. And which distribution should you use and why? We're using the T because the standard deviation is unknown. And they want a 98% confidence interval for the mean number of hours. Okay, so that means that alpha is equal to 1 minus 0.98 or 0.2. So alpha divided by 2 is 0.01. So we're going to need that. Okay, let's go to Desmos and find our sample mean and sample standard deviation. I encourage you to try this on your own. Let's go. This is example 4. So there's our data. So our mean is 6.133. And then sample standard deviation is 5.14448. And then our T, because alpha divided by 2 is 0.01, so our T is 2.62. And so we're calculating our error bound of the mean right here is 3.7358. And then we're calculating our lower and our upper. So our confidence interval is 2.39 hours of TV up to 9.87 hours. That's a pretty big range. And that's because we're so confident. Remember, the higher the confidence, the wider the confidence interval. So let's go ahead and just see that in our formula here. So if we used our little computer program, we type in sample size is 15, and then average number of hours of TV for the group was 6.133. And the standard deviation was pretty big because of that. Ones didn't watch 20 hours, and the other one, there were 2 other ones that watched 10. And then our alpha is 0.02. And so our lower is, we can see it's 2.396 and 9.87. So this little formula program is quick and easy to use to validate everything. And to do it quickly, because it gives you your error bound. It gives you your lower and upper quickly. Together for example 4 again. And here's our error bound. And then this is pretty big this time, 98. So we only have 0.01 over here and 0.01 over here. And this T is 2.62, and this is a negative 2.62. So we are 98% confident the true number of hours that statistics students spend watching TV is between 2.4 and 9.9 hours. Example 5. Example 5 says a hospital is trying to cut down on emergency room wait times. It is interested in the amount of time patients must wait before being called back to be examined. An investigation committee randomly surveyed 70 patients. The sample mean was 1.5 hours with a standard deviation of 0.5. So let's kind of fill everything. And so we have N is 70. So degrees of freedom is 69. The average was 1.5, standard deviation is 0.5. X is individual wait time in hours, and this is the average wait time for sample. And again, we're using the t distribution because the sigma is unknown. Construct a 95% confidence interval for the mean time spent waiting. So our alpha is 0.05 and alpha divided by 2 is 0.025. So our t of 0.025 and 69, right? We're going to find that in so our t distribution, our t critical t is 1.995, and our error bound is calculated here, and that's 0.119. You can see that here. Just put okay, And then there's our lower bound and our upper bound. So 1.38 and 1.62 hours. Okay. Let's go back to the paper so we can document all that. This is I'm not drawing that picture. This is 0.95, and out here is 0.025, 0.025. Positive. So it says we are 95% confident the true population wait time in the ER is between 1.38 and 1.62 hours. So notice our confidence is less than the last one, and then it does seem like our confidence interval is much skinnier, and that's why. So the higher the confidence, the wider the confidence interval. The lower the confidence, the tighter the confidence interval, the more accurate you are. So our last example for 8.2 is example number 13. And we also have this documented in Devmos. So it says, suppose that a committee is studying whether or not there is waste of time in our judicial system. It is interested in the mean amount of time individuals waste at the courthouse waiting to be called for jury duty. The committee randomly surveyed 81 people who recently served as jurors. The sample mean time was 8 hours with a sample standard deviation of 4. Okay. Oh, this should be. Okay, so the sample mean time was 8. Sample standard deviation was 4. There were 81 people, and so degrees of freedom is 80. So this would be individual wait time in hours. And this would be average wait time for the sample. Again, we're using the t distribution, and that's because sigma is unknown. And we're using we're constructing 95% confidence interval. So we're looking, so alpha is 0.05. Alpha divided by 2 is 0.025. So the t of 0.025 and 80, we'll find that in decimals. So let's go there. That's 1. And there is 9.99. And there's our error bound of the mean, 0.8844. And there's our lower and our upper, 7.9 7.11 and 8.88. It's really should be 7.12 rounded right here. 7.12. Okay. And again, you can see from our formula here, we could go up here and enter in our sample was 81 and our sample size. Sample mean was 8. Sample standard deviation was 4. And our alpha was 105. And there is our confidence interval. And always validate your confidence level right here. Okay. So let's wrap this up. So there's our error bound margin. And our graph here is our 95% confidence. So there's 0.025, 0.025. There's our confidence interval. So we are 95% confident that the true population wait time for jurors is between 7.12 and 8.88 hours. That's a lot of hours to wait to be called back. I think they're trying to get more efficient with that. So that wraps up confidence intervals for means when we have an unknown standard deviation. So catch me back for lesson 8.3. We're going to do some confidence intervals for proportions.